Thank you. Thank you for the presentation and for the invitation. So I'm going to talk first about fluctuations for linear eigenvalue statistics, but for Wigner matrices, and then for Wigner matrices deformed by an additive perturbation, and then for polynomials in Wigner matrix and a diagonal deterministic matrix. So first I would like to fix some notation. So I will take a Wigner matrix with IID random with IID entries and well, with several assumptions on the moments. So I suppose that the variance of the entries converges to some parameter, so the most important is sigma squared. We ask for the second moment of the entries to converge to a parameter theta, which will be a real and not a complex number. And the fourth cumulant of the off-diagonal entries converges to a parameter kappa. So the assumption on theta just say that actually the imaginary and real parts of the entries are uncorrelated, but you can have different variances. But for this talk, I will assume that this parameter theta is 0. So actually the real and imaginary parts of the entries are uncorrelated and have the same variance. So just to simplify, you can think that they are IID variables. So we denote by lambda 1, lambda n the ordered eigenvalues of the normalized Wigner matrix. So Wn will always be the normalized matrix. And we know by the Wigner theorem that if we take a test function which is bounded and continuous, we have the convergence of the quantity here to the integrals of phi with respect to the semicircular distribution with a variance sigma squared. Okay, so what is called the linear eigenvalue statistic is this quantity. So it's a trace of the function phi applied to the matrix Wn. Okay, so it's quite a natural question to ask for the fluctuations. And actually, the question of studying the fluctuations of this linear eigenvalue statistics around its deterministic equivalent, which is here, is really often decomposed in two questions. Sorry. The first fluctuations around the mean, and then studying the bias. Okay, so this talk will be mostly about the fluctuation around the mean. So there have been lots of work on this question. As far as I know, the first work on fluctuation for linear eigenvalue statistics was carried out by Johnson in the 80s, but for the covariance matrix model. So there are plenty of, lots of papers for this model and other model, but for the Wigner matrices, I think that the first work was done by Sinai and Soshnikov at the end of the 90s for a specific test function, so the x to the k. So there has been several works during from 2001 to 2022, I think, the more general one. And so the idea was to step by step reach more and more general test functions and weaker assumptions on the entries of the Wigner matrix. Okay. What I would like to say is that in most of these works, but not all of them, the first step is to prove, well, to compute the fluctuations for specific functions of this form. So you take a complex number z which is not real, and you consider this function 1 over z minus x. And after that, you extend the result to more general functions. Okay, so now I can state the result for Wigner matrix. So just note that the result is written in the case where sigma squared equals 1, because the formula was just too big. But you can just deduce them by a change of variable. So you have that for Wigner matrices, the fluctuation of the linear eigenvalue statistics around the deterministic equivalent are asymptotically Gaussian, and you have an explicit mean and variance which are given by these formulas. So, as usual in random matrix models, the variance of the linear eigenvalue statistics is of order 1. You see that you don't need any normalization to make this quantity converge. And so it's really far less than what would be expected for the classical TLT if the particles were IID points in R, okay? And from the expression of the limiting variance, you can see that it's clear that you need some regularity assumption for phi, because this fraction here can behave really badly when x and y are close. Okay. And so I think that the best result is due to London and Soso, and they have the result for a function in the space h1/2 plus small epsilon. Okay, so with Maxime Février, we were interested in the deformed model. So you take a normalized Wigner matrix and you had a deterministic diagonal matrix. So you suppose that it has an empirical spectral distribution which is denoted by nu n. And you suppose that this nu n goes to a probability measure nu. So Pastur proved in the 70s that the empirical spectral distribution of xn, the deformed model, goes to a deterministic probability measure. I will denote it by rho, but it turns out that it can be described as a free additive convolution between the semicircular distribution with variance sigma squared and the nu, which is the limiting distribution of dn. Of course, this gives the convergence of the normalized linear eigenvalue statistics, and we ask for the fluctuation, but well, till around the deterministic equivalent of this linear statistics, so which involves the free convolution of the semicircle distribution with variance sigma n squared and the empirical spectral distribution of dn. Okay, sorry. I must say that the same question was that G and Lee became worked on the same question approximately at the same time for the same model. And so they proved this theorem, and we had a very similar result, but with slightly different assumptions. So at the end, we got that the centered linear eigenvalue statistics fluctuates asymptotically like a Gaussian variable as soon as the test function is smooth enough. So, for example, C2 with compact support. So, as I said before, the first step is to prove the result for this specific function phi of z, which is quite natural because in this case, the linear eigenvalue statistic is equal to the Stieltjes transform of the empirical spectral distribution mu n. And in this work, we make use of the strategy which was developed by Yao, Silverstein, and their co-authors to work on these questions. So first, the problem is reduced to the case when the entries are bounded by something which goes to 0 but really slowly. So you have to truncate and renormalize the entries, but okay, it's not difficult. And the main point is to prove the convergence for this specific function phi of z. And then by Yao and Silverstein and Ji and Lee first used this approach, they extend the results for analytic function using the Cauchy's formula. So we are doing approximately the same, but we use another extension argument to reach a less smooth function. And this argument is due to Sherbina. Okay, so I want to begin with the case of the function phi of z. So I won't show you all the computation, but I want to show you the beginning. So first, we know that this linear eigenvalue statistic is still just transform, so you can write it at the trace of the resolvent. Okay, so you can use computation on the resolvent matrix. And we want to use a Martingale argument. So we want to write this centered linear eigenvalue statistics as a sum of difference of martingales. The idea is to use the central limit theorem for this difference of martingales. So we introduce the sigma field f k. So it's just need small. So when you take your matrix W, you consider the top left submatrix of Wn with size k by k, and you condition with respect to the entries in this submatrix. Okay, and so as the sigma field grows, you got a filtration, and then you can define a martingale simply by conditioning the trace with respect to this sigma field. Okay, so to use this central limit theorem, we have to prove first that the condition, which is called the Lyapunov condition, is true. So it's not difficult, and it is due to the assumption on the entries. And the main point is to prove the convergence of the so-called hook process, which is defined right there. So we have to prove and compute, to prove that this quantity gamma n converges, and to compute the limit, because if we prove this, we know that the sum of this Martingale difference will converge in a finite dimensional distribution to a Gaussian process with this covariance function, with the gamma function. Okay. And we have to do this for all d1 and d2 complex numbers which are not real. Okay, so just recall the expression of the delta k, which is the difference at step k. And the main point is to note that the only difference between fk and fk minus 1, just write k minus 1, lies in these entries. So if you can, well, if you can write this trace with some terms, but some of them do not depend on the entries there, then this part will disappear in the difference. Okay, so this is the main idea. Just start with k equals 1. And I write the matrix xn as usual as this matrix x1, which is at the bottom right. You just remove the first line and first column. You have here the entry x11, and c1 is the vector you get here by removing the first component. Okay. And here you get c star. And use the Schur complement formula to get that the trace of the resolvent is equal to the trace of the resolvent of this matrix plus some term, which is not really complicated. You can do the same for general k. So we get this result, and if we work a little bit more, at the end, we get that we can write the trace as a first term tk, which will not depend on the entries on the line k and column k, a middle term, and a small, well, this term epsilon k will be very small, and it will not wait in the limit. Okay, so all we have to do is to deal with this middle term, which can be written quite easily as a derivative of a quite nice expression. So we can replace, in our Hooke process, we can replace delta k by the difference, but where we put psi k of z instead of this delta k. So we, with this idea, we could compute the limit. And at the end, what we get is that the centered trace of the resolvent converges to a centered Gaussian process with explicit covariance function. And what we get is the following. Okay, so the exact expression is not really important, but I wanted to put it because it will be something very similar for the polynomial of Wigner and deterministic matrix, except that it won't be scalar anymore, but there will be a matrix coefficient. But what can we say about this formula? I'm sorry, I didn't say that omega of z is defined here, where you have the Stieltjes transform of the limiting law. And it's called the subordination function. And okay, so what we have to, but it's not really clear when we get this result is that this logarithm is well defined. Okay, because this quantity is a complex quantity, and so you have to prove that this thing is less than 1 in modulus, but actually it's not that complicated to prove that, and it's true. So the logarithm is well defined, and the covariance function is well defined. So we got the result for the specific function phi of z. Now we want to extend it to a more general function. And as I said, we make use of a theorem by Sherbina, who proved that if there exists a certain normed space of test function, which will be denoted by L, such that the following is true. So for any function in L, you can bound the variance of the linear statistics by a constant times the squared norm of the function in this space. Okay, so you suppose that you have this bound, and you suppose that there exists a dense subspace L1 in L, such that you have the result, so you have your CLT, which is true for these specific functions. With a limiting variance here, which is continuous in the test function phi. So if you have that, then you can prove that there exists a unique continuous extension of V, the limiting variance to all the space, and that the central limit theorem is still true for every function in L. Unfortunately, it does not give an explicit expression for the extension. Okay, but we know that it exists. So for the dense subspace, we will take the subspace generated by the function phi of z. Okay, so we had the convergence of the process of this linear spectral statistics for the phi of z. So we know that the result, the CLT, is true for this function. And it appears that this subspace is dense in the Sobolev space H of S, which is the space of all function phi which are square integrable, such that this quantity here is finite. So here, phi hat is a Fourier transform of phi. So what it says basically is that you have to have a Fourier transform which decreases fast enough at infinity to get this quantity to be finite. And Sherbina proved that you can bound the variance of the linear statistics for all function phi in this Sobolev space by a constant times this square norm times a quantity here which depends on the variance of the linear statistics, but for a function phi of z. But you have to control it in terms of the real and imaginary part of the complex number z. It turns out that it's not difficult to bound the integral on the variance with respect to x, and you can bound it by a constant times over y to the 3 plus epsilon, where epsilon is small enough. And if you put this in the bound, you get that the quantity will be finite as soon as S is greater than 3/2 plus a small epsilon. And this space contains, for example, the compactly supported C2 function. So the result is true for these functions. Okay, but as I said, we do not have any explicit expression for the limiting variance by this strategy. But I must say that using the Cauchy formula does not give an explicit formula either. So. Okay, I said that I won't talk about the bias, but just a little bit of information about it. So you can consider the expectation of the linear eigenvalue statistics, and you compare it to the deterministic equivalent. It's possible to prove that it converges for the specific function phi of z, so for the trace of the resultant, and by a density argument very similar to the preceding one, you can prove that this convergence is true for more general function, but not as well. You need more regularity than for the centered fluctuation, and you get that essentially it will be true for compactly supported C7 function. Okay, so now obviously the deformed model is a specific case of when you take a polynomial in Wn and Dn. So why not just have a look at the same question but for a self-adjoint non-commutative polynomial in two variables, which we will apply to Wn and Dn. The trouble is that the computation, well, we want to use the same strategy, and the trouble is that the computation for the to prove the convergence of the trace of the resolvent for the deformed model makes repeatedly use of the fact that the deformed model is linear both in Wn and in Dn. So there is a quite classical trick, and in some way we can make this polynomial to be linear at the cost that we have to replace the scalar coefficient by a matrix coefficient. So the idea is following that we will compare we will relate the idea of the linearization is to relate the spectrum of a nonlinear polynomial with scalar coefficient to the spectrum of a linear polynomial but with a matrix coefficient. Okay, so here is the definition of the linearization. So linearization is a matrix with coefficients which are polynomial in, I wrote it for two variables, but it's okay for any number of variables. And you ask the matrix Q, which will be of size m-1, to be invertible. And so U is a row vector, V is a column vector of size m-1, and you ask for U, V, and Q to have at most degree 1 in T1 and T2. Okay. And we ask for P to be equal to this quantity, and this is a linearization of our polynomial. So we can write it Rp as using the tensorization. We can write it as follows. So we have a matrix coefficient. So gamma 0 is m by m, tensor 1 plus a coefficient gamma 1 tensor T1 and a coefficient gamma 2 tensor T2. An example. You can just check that this thing is really a linearization for the polynomial P, which is written here. And Anderson proved about 10 years ago that any self-adjoint polynomial P has a self-adjoint linearization, so it's not unique, but he gives an explicit algorithm to compute a specific linearization, which we will call the canonical linearization. So in what follows, I will always consider the canonical linearization. And I have to say that this linearization is not a canonical one for this polynomial. It gives a much bigger matrix, but it gives a way to have a linearization. Okay, so that's good, but how can we relate the trace of the resolvent of our polynomial in Wn and Dn to this linearization? Okay, we write this linearization in Wn and Dn, and what we want to study is this quantity, so is this the trace of this matrix, which is of size n by n, okay? And we want to relate this quantity with this thing, which I've written it with tensor, but you can think about it as a matrix of size m times n. No, mn, sorry, by mn. Okay, and you can prove that if you consider this resolvent of the linearization that you evaluate at this point, you can write, it's a big matrix, so I will call it the big resolvent. So it's in the big resolvent, what you can see is at the top left n by n block is the resolvent that we want to study. Okay, so if we, sorry, just the matrix E11 is this one, so you just put a 1 in the 1, 1 coordinate and 0 otherwise. So just to keep this, we want to keep only this. We want to express the trace of this quantity with something with this. So we multiply this big resolvent by this matrix. So it's E11 tensor, the identity matrix. And if you do that, you can see that you will have, on the diagonal, you will have only 0 except for this quantity which will remain unchanged. And if you take the trace, then you get that the trace of this quantity writes as this trace of the big resolvent multiplied by this quantity. Okay, so just by this we can relate both spectrum. And from this observation, we can essentially carry out the same computation as in the linear case, but instead of scalar coefficient, we have matrix coefficient, matrix of size m. So the problem is that with scalar, everything is quite easy, but here when you have matrix coefficient, you have some commutativity problem and you have some invertibility problems. So it was a bit more difficult than the linear case, but at the end, what we get with Serban, Mireille, and Maxime is that the trace of the resolvent for the polynomial, when you centered it, it fluctuates, it converges to a Gaussian process, a centered Gaussian process with an explicit covariance function gamma. So now I want to try to write explicitly the function gamma, so I have to introduce something. So using really the same machinery as in the linear case, we can write this function gamma as a derivative with respect to z1 and z2. It's really the same as in the linear case. Okay, so recall that in the linear case we had this formula with omega of z, which write as follow, and which is a subordination function. So I will have a quantity which is similar, but here we have a complex number which will be replaced by an operator. And I need to introduce a subordination function, but with a matrix valued coefficient. Okay. So I take x and d, two free non-commutative variables in some space with x has semicircular distribution with variance sigma squared, and d has its distribution is nu. And if you take a matrix beta of size m, such that its imaginary part is strictly positive, then you can write this subordination function as follows. Okay, so it's a bit complicated expression, but you have an explicit expression. Okay. So It's supposed to exist only for beta with positive imaginary part, but actually it may be proved that it extends because we need to evaluate it at with beta equals z e11 minus gamma 0, which has not a positive imaginary part, but it can be proved that it can be extended as an analytic map for this z as soon as you're not in the limiting support of the measure. Okay. When I have this, I can define this operator. So you fix two complex numbers z1 and z2, which are not real. And you have this operator, which is defined on the product of matrix of size m with matrix of size m of this integral. Okay, it's a bit complicated, but if you watch it, if you look at it, you can see that here on the left part, so you have an integral, and in the left part you have something which is close to the omega of z1 minus x that we had in the linear case, and here you have something which is approximately the omega of 1 over omega of z2 minus x in the linear case. So just here. This is an analogous formula for this quantity. Okay. At the end, we will have the logarithm of something which involves this operator, and we have to prove that it is well defined. Okay, so it was quite a hard task, so it was Serban's work. And I confess that I don't understand anything about what he did, but it works. And he proved that the spectrum of this operator is included in the open disk of radius 1 over sigma squared. So when you multiply this operator by sigma squared, you can define this logarithm, which is written here. And at the end, what we get is the following formula for the limiting covariance. Okay, so the limiting covariance is the derivative with respect to z1 and z2 of this quantity. Okay, and so you see that you have a very similar expression than in the linear case. You can really relate each term to a term in the linear case. So you have this logarithm, and then this term which depends on the force cumulant, and which is also very similar to the one in the linear case. Okay, so at this point we could not manage to extend the result for a more general function, but we were quite satisfied with this. So I thank you for your attention.